So today we are going over lecture 1 into my 10 lecture series for calculus. And today we're going to start off with lecture 1, the foundations and the building blocks of what you need to know to start learning calculus. So the goal for today, we're going to go over some notation. We're going to go over domain and range, and we're going to go over some simple graphs. And a lot of this should be review. And then I'm going to move on to y2 minus y1 over x2 minus x1, the equation to calculate the slope. And we're going to see how that relates into derivatives. And we're going to use a little trick utilizing limits. And because of that, I'm going to introduce the limit to you and how we use it. And I'm going to start everything off with some basic questions. And hopefully by the time we're done, you have a simple idea or you have a basic understanding of calculus and the building blocks of calculus. So I like to start this segment off with a question. If you drive 120 miles in 2 hours, your average speed is 60 miles per hour. But your speedometer at 1 p.m., for example, might read 73 miles per hour. What does that 73 miles per hour even mean if it's measured at a single instant with zero elapsed time? This question was asked, and people weren't too sure how to solve it, but calculus was invented to solve this type of issue. It's intended to solve what happens within those 2 hours. You're not driving 60 miles per hour. You need to start off at zero. There's like red lights, you need to stop occasionally. You might speed up, you might slow down. What calculus does is that it solves what is happening at that instantaneous time. For example, at 1 p.m., if it reads 73 miles per hour, you could be speeding up or you could also be slowing down. It just really depends on the situation given. And calculus is what breaks everything down. So to start things off, we can start off with a simple notation question, and I'm going to go over what f of x means. So we write f of x by writing the letter f and then x in brackets, and this means the output of function f when the input is x. So as you can see, the output of the function at the letter on the outside, we normally denote as f, which just stands for function. And if you remember, you could be putting some value into that function and it'll output something. It could be some equation, some expression, something like that. I'll show you this with a more concrete example. For example, let's set f of x to equal x squared minus 2x. We're given some formula and we can plug in anything. This is what I mean by the input is x. X can be any value. It doesn't have to be just a number, it could be an expression as well. So that idea is really useful later on down the line, but for now we can just do some practice. So let's evaluate this. At f of 0, f of 2, and let's do f of a plus 1. Notice how the first two are values. The values of the first two are a number, whereas the third one is an expression. It doesn't have to be just like a 0, a 1, a 1.5, for example. So the way you solve this is just that the 0, you plug the 0 in. So starting off with f of 0, you pretty much just plug in the value 0 into everything that goes into x. So this will become 0 squared minus 2 times 0. And if you can evaluate this, this will become 0 squared is 0, minus 2 times 0 is 0. And as you can see, the input x, you just plug in whatever value into the variable x within this equation. So let's say there's another variable y, like let's say z. You would only fill in x, you would only fill in the value which you input as x into the x, not the z. Okay, let's try f of 2. Again, the equation is x squared minus 2x. And because you're replacing the x's with the 2's, you would get 2 squared minus 2 times 2, which would equal to 0 again. You can plug in different values and you can still get the same answer, but they're also completely different. They're also completely different functions. Now let's do f of a plus 1. Again, we're plugging a plus 1 into x, so we would get a plus 1 squared minus 2 times a plus 1. So we can expand this out just to show you what it'll look like. It will be a squared plus 2a plus 1 minus 2a minus 2. Again, we can combine the like terms, so we have a squared, 2a minus 2a is 0, 1 minus 2 is negative 1, so we're left with a squared minus 1. And that is showing how the input doesn't have to be just a number, it could be some expression as well. Okay, the next section we're going to go through is the domain and range. And what the domain and range is, the domain of a function is a complete set of all possible input values for the x. So domain is the complete sets of all possible x values. Now the range is the same thing, but it's all the possible output values, so it's the y values. The sets of all possible It is the set of all possible output values, aka the y values. I'll rewrite this to match it, sorry. All possible input values, x values. And I'll show you this with a simple example. For example, we have the function f of x equals to 1 over x minus 3. So we know that we cannot divide something by 0. It is undefined. It does not exist. So we know that, we can see that the domain excludes 3. So this could be like a hole or a break in a graph, and I'm going to show you that visually. So we have some x and y coordinate. Let's set this to be 3. The way this looks, if you were to graph it out, it'll be some graph looking like this, if you remember from pre-calc. So as you can see, the graph moving from left to right, it will never touch x equals to 3. There's a break in the graph, there's a hole, because this function will never exist as it gets at 3, but it will exist to the left and to the right of 3. And I'm going to use this graph as an example to further solidify the beginnings of calculus. Is that if I gave you this graph and I were to ask you, is it increasing, decreasing on an interval? Where is it steepest? Where does it look flat? And if I asked you which part of the curve is changing fastest, how would you show me that on this graph? And would you pick a point, or would you describe the graph as a whole? Again, if you remember the car example, the miles per hour example, if I were to ask you at this point, is this graph steep? Is this at this point in the graph, is it changing fast? Is it fast? If I were to look at it, it seems pretty flat. So the curve itself isn't really steep. If you calculate the slope, if you were to calculate the slope at this point, the slope would be something like this, right? And it's not really steep, so that means the slope is pretty slow. It's not fast. If I were to ask you at this point, how would the graph look? Well, the slope looks like it's going down. Maybe we could say something how the speed is increasing negatively. We could say something like that. If I were to ask you the slope here, we see that the slope is almost vertical. What would that tell you? The slope is decreasing on the interval, but it's also extremely steep because it's almost vertical. So we could say that the change of the curve is extremely fast and the steepness is really steep. I think that's a pretty basic demonstration of domain and range, and a little bit of an introduction to the steepness of a graph. Next, I'm going to go over the average rate of change. So just to reiterate, the slope between 2 points, x1, y1, and x2, y2, is y2 minus y1 over x2 minus x1. The only thing we're changing is how we write y, and we're going to write y in terms of f of something. In this case, we can use a and b. So if I were to write that, we could write something like f of b minus f of a. I'm just replacing x and y with a, just so that it's a bit easier to not confuse y with f of x. So we have f of b minus f of a over b minus a. This is exactly the same slope formula. It's just new notation. There's nothing new mathematically yet. So let's do a practice example. For example, we have f of x equals to x squared. I want to compute the average rate of change of f of x equals to x squared over progressively smaller intervals starting at x equals to 1. So let's look at the interval 1, 3. I'll quickly draw a graph just to show you what's going on. So we have some xy coordinate. And if you remember x squared looks something like this. A shape is a parabola. And in this first example, we're looking from the range x equals to 1 and x equals to 3, something like this. So I was looking within these ranges. I was asking what is a slope. So again, if you were to do this without the, just by using y2 minus 1 over x2 minus x1, you would just draw a point at x equals to 3 and x equals to 1 and calculate the slope of the line like that. So let's do that. So we would do, so y2 would be 3 to the power, 3 squared would be 9. 1 squared would be 1, so we have 9 minus 1 for the top part. Actually, I'll be a bit more clear. So I'll rewrite this as f of b minus f of a over b minus a. So where f of b comes from, f of b, we're taking the function f of x and we're replacing x with 3. In this case, b is 0.3 and a is 1. F of b pretty much is just y2, so in this case, this 0.39 is, the coordinates would also be 9, 3, and 1, 1. These are the 2 points here. I know it's not really drawn to scale, but it's just a demonstration purpose. So where did the 9 come from again? I would just plug at x equals to 3, so I put 3 into, or put 3 into here. Hence we put 3 in for x. 3 squared equals to 9. So now we have 9 minus f of a, so just 1 squared is 1, b minus a, so again we just take the point here, this is b, 3 minus a, which is 1, equals to 8 over 2, which equals to 4. So we see that from this point to this point, the slope is 4. I'll show you one more example where let's see what happens when we decrease the interval. So let's try, I think I'll use less space this time, 1, 2. Let's see what happens when we decrease the distance between b and a. So just quickly going over it, f of b would equal to 4, because 2 squared equals to 4. So we would have 4 minus 1 over 2 minus 1 equals to 3 over 1, which equals to 3. I wanted to quickly go over why am I emphasizing shrinking the distance between a and b. Why am I fixated on that change in x? Well, we're going from here to here. This delta sign just means change in. So it's really as simple as just like, what is the change from going from this point to this point? Well, you just simply find the distance, and you can do that by subtracting the second point by the first point, and it'll give you the distance between that change in x. If we see that the slope between these 2 points is like this, something like that, we see that it pretty much resembles the actual slope, the blue line, right? We see that it's pretty similar. Now, what if we keep decreasing that delta x? If we keep decreasing that delta x, we're going to get closer and closer to the truth of what that point on that curve is. because a curve is never straight, so you can't really calculate the curve. You can't really calculate the slope of a curve. But what we can do, we can keep shrinking and shrinking that delta x until we get something called a tangent. And what a tangent is that it tells you the slope on a singular point on a curve. And it is when there is one point of contact between a curve and a line. And that point is called the tangent. And that will also tell you the slope or how steep a curve is. And it becomes really important in calculus. And again, just to reiterate, we find the tangent by taking that delta x and we keep decreasing that gap. You want to take the limit as delta x approaches 0 because you can't really take the slope at a point 0. You have to incorporate limits, which is what I'm going to go into next, to help shrink that gap and to find that tangent. So before I go any deeper, I'm going to start talking about limits and just like a really basic idea of what a limit is. So let's try the example g of x equals to x squared minus 1 over x minus 1. Notice that at g of 1, it is undefined. So let me write that neater. Because if you plug in 1 for x, you would get 0 over 0, which you simply cannot evaluate. But we're going to ask, what does g of x do as x gets very close to 1 from both sides? So you can think about like some number line at point x equals to, let me set this as 0, we'll set this as 1. We know at 1 it's undefined, it doesn't exist. But what happens when we approach 1 from both left and right side? So we can use numbers like something really close to 1. What if we use something like 0.999 from the left-hand side? Or from the right-hand side, what if we use 1.001 or 1.000001? We're not at 1, but we're really close to 1. So let's try plugging in numbers and see what happens. Given some chart x and f of x, at x equals to 0.9, 0.99, 0.999, and from the other side, we have 1.001, 1.01, 1.1. That's a really messy graph, but if we plug 0.9 in for x, we would get 1.9. If we plug 0.99, as you can see, 0.99 is closer to 1 than 0.9, we'll get 1.99. So on and so forth, we'll get 1.999. What if we approach on the right-hand side? If we plug in 1.1, we would get 2.1. 2.1. If we plug in 1.01, we would get 2.01. If we plug in 1.001, we would get 2.001. Do you kind of see how as we converge closer to 1, we notice that if we converge closer to 1, do we see how we approach to the number 2? Both sides are sliding towards 2, even though x equals to 1 itself is a forbidden input. And this is a key idea. A limit describes behavior near a point, not exactly at the point, and it kind of helps describe what is happening at that point. And I think this is a pretty good introduction to what limits are, and these are the building blocks to what will eventually lead to your understanding of calculus. My plan for these lectures is that I'm going to provide questions and I'm going to provide a deeper dive into everything I went over today. I want to go over how to derive the equation of a line again, but in a calculus format, and I plan on expanding further into limits in the second lecture, and second and third lecture. And if you have any questions, please feel free to comment down below in the description, and I'll try to get a reply to you as soon as possible. Thank you.